Okay, thanks a lot for the invitation. Certainly would love to visit IIS again sometime. So I will talk about some recent work with Sam Lusser. Sam actually will be at Princeton in the fall, so he's very excited. When we talk about quantum gravity, so one of the first problem arises is the say so-called problem of time, because in quantum mechanics time is absolute, but in gravity most of the time is just a coordinate, and it can be changed by arbitrary gauge transformations. So it's hard to assign invariant meaning to it. But in some cases, for example, in ADS, things are a little bit special because here there's a absolute asymptotic time. And of course, this is the reason that actually underlies the success of the ADS-CFT. And this is also the reason why quantum gravity in space-times of other asymptotics appears much more difficult, because such a absolute asymptotic time does not seem to exist. So even in the context of ADS-CFT, we can ask the question, how do we understand the Bach time evolution? Okay. So in cases, if you have a global time-like Killing vector, say if the corresponding boundary state is time translation invariant, and then the situation is much simpler, because now in this case, there's preferred time slicing in the Bach. So we can actually extend this boundary time, say, to the interior. But in general, the situation is much more not clear. Okay. So this makes the internal black hole a particularly interesting example, because this is something in between. So yeah, so from Huan's a paper in 2001, it was conjectured that physics, say gravity in this internal ADS black hole space-time is dual to two copies of your boundary CFT in the thermal field double state. Okay, there's no interaction between the two CFT, but they're in the entangled state. So this example is interesting because there is time-like Killing vector outside the horizon. And so, so you can separate this black hole into, say, R, L, future and past regions. And so for region R and L, we can actually extend the boundary time, say, to the Bach without much effort. So the physics outside the horizon can be understood using the standard ADS-CFT story. But this time stops at the horizon, okay? And in the future and the past region, there's no time-like Killing vector. And so that's essentially underlies the difficulty to understand those regions from the boundary. Okay, yeah, so there are many mysteries associated with the horizons and the interior regions. Say, how do we understand future and past regions? How do we understand the Kruskal-like time from the boundary theory? And also, how do we understand from the boundary, the horizons and associated causal structure? Furthermore, say observers, say in the R and L region, they can fall into the horizon and intact in the future region. So that seems, again, also cause a puzzle, because the CFTL and the CFTR, they are non-interacting in the boundary theory. So our goal in this talk is to give you a boundary construction, say, of Kruskal-like evolutions. And such a construction will help us to understand, say, boundary emergence of horizon, interiors, and also the associated causal structure. So here is the plan for today's talk. So first I will talk about the emergent type III1 von Neumann algebra structure, and that will have some important implications. And then I will use that to discuss how to construct Kruskal-like time evolution from the boundary. And then I will say outline the main results, and then maybe offer some discussions. So as I already mentioned, that the internal, say, black hole in ADS is described by the CFTR and the CFTL in the thermal field double state. So here I will always consider the theory on the sphere, okay? And also I will always consider the temperature is above the Hawking page transition. Yeah, so that the theory is just due to the, corresponding to the, the thermal field double state above the Hawking page transition. And at the finite n, the operator algebra, say in CFTR or CFTL, is the standard type 1 von Neumann algebra. So this is trivially because you have a Hilbert space, tensor product structure of Hilbert space associated with CFTR and CFTL, and then this is just the standard operator algebra. But to understand the classical gravity description, we actually need to consider the boundary theory in the infinite n limits. So in my talk, I will use these two language exchangeably. So you either consider infinite n limits, or you consider finite but large n, but we do 1/n expansion. Okay, we do asymptotic 1/n expansions. I will view this two procedure as the so what I say can be applied to either cases. So in this case, most of the many operators in your original or operator algebra, actually they don't have a well-defined RGN limit. So those operators which have a well-defined RGN limit, so we can be viewed as algebra, say generated by single trace operators in CFTR. So by single trace operators, we mean those operators whose definition don't depend on n. Okay. And then the algebra generated by the sum and the standard product of such operators, they form algebra AR in the infinite n limit. And also in the infinite n limit, you can define some of your double states, say as a normalized positive linear function from the algebra, from this single trace operator algebra to complex numbers. Okay. And so this state can be defined, has a sensible definition. And then we can also talk about small excitations, say around the thermal field double states. And in the large n limit, it turns out they actually, such small excitations around the thermal field double state, they actually form a Hilbert space. Okay, so so heuristically, we just act, say, product of those single trace operators on the thermal field double states, and but mathematically, you can show that actually that has a structure of a Hilbert space using this so-called GNS construction. Okay, so we just call this a GNS Hilbert space around thermal field double states. So now if you look at the algebra, so this algebra generated by single trace operators, it's abstract, you can view it as abstract algebra. But then on this GNS Hilbert space, this Hilbert space around the thermal field double state, it can have a representation. So we denote the action of this single trace operator algebra in this GNS Hilbert space MR. So emphasize this MR I emphasize this because the different AR acting on the different, say, the Hilbert space may have its algebraic structure may have different nature. Okay, so I use a different name MR to denote the representation of AR around this thermal field double state. Okay, and so the proposal then is that in the large n limit, so you can also similarly define such algebra in the GNS Hilbert space for the single trace operator in the CFTL. So the proposal is that this MR and ML are type III1 von Neumann algebras. So I will not have time to review the definitions of von Neumann algebras as well as the classifications of von Neumann algebras. And let me just mention the type III1 von Neumann algebra is one we often encounter in considering local operator algebra in quantum field theory. So any questions so far?
So yeah, I have a question, huh? It's Greg. So are you assuming those type 1 algebras are simple?
Sorry, what do you mean by simple?
I mean,
you mean the factor?
Full matrix algebra instead of a direct sum of matrix algebras. In other words, you could imagine having blocks, matrices where you only allow blocks along the diagonal.
Right.
That would not be simple, but it would still be an algebra, and it's perfectly
right.
good.
You're asking whether such algebra has factors. Yeah. Whether they're factors. Yeah. I think they're not factors because they have like they have non-trivial centers. Yeah.
All right. So I mean, why? Well, I mean, it's kind of a standard thing to take limits of type 1 algebras and get type 2. Like you take a Bretelli diagram, and then you can nicely get limits of type 1 algebras, get a type 2 algebra. That was fun, all that stuff that von Jones did.
Okay.
So why type 2, why type 3 and not type 2, for example?
Yeah. Here I will explain. Yeah. So this type III1 is really come from the large N structure. I will not explain in detail. I will mention just why. I mention some motivation why this is type III1. Yeah.
So Hong, just to be clear, when you say that the algebra is type III1, you mean that each of the factors in the direct sum decomposition is type III1? That's
right. Yeah. So those. So I'm not saying they're. So this MR and ML they're not factors. Likely they're not factors. And they just say they involve the sums of the type III1 algebras. Yeah.
And do you want to tell us whether it's a direct sum or a direct integral, or whether the direct sum is finite?
Yeah. For our purpose, frankly, I'm not sure myself. But for our purpose, that will not be very important.
Okay. Thank you.
I think the expectation from the bulk point of view is that it's a continuous integral. For example, the area should be in the center.
Mm-hmm. Yeah, I think it's a reasonable expectation. I don't know for sure myself. Yeah. Okay. Other questions? Good. So there's some support we can offer for this proposal, but I will not have time to go into detail of those support because so the first one is by looking at the thermal spectral function of the thermal single trace operators. So the reason that this is relevant because this GNS Hilbert space is defined in terms of the 2-point functions, say of single trace operators in the thermal field double state. And so the structure of those inner product actually determines the algebraic structure. And so the behavior of the thermal spectral function is actually relevant. Okay. Yeah, so we're not going into detail here. You can look at the paper. And the second is we can show that actually those algebras allow this half-sided modular inclusion or translation structure, which I will mention in more detail later. And this only occur for type III1 von Neumann algebras. And the last one, which is the most simple to describe, which I will describe in some detail. So this is based on the duality with the Bach, just based on our standard duality, say outside of right. So now let's consider the Bach theory in the G Newton goes to 0 limit. Say we can consider either the leading order in the G Newton goes to 0, which is a free theory, or just perturbatively in the G Newton. So in the Bach theory, then that can be formulated as a quantum field theory in the curved space-time. And so here you can say define your standard Hartle-Hawking vacuum for the internal black hole, and then you can use the fields, say metric and the matter fields on the gravity side to build a Fock space on this Hartle-Hawking vacuum. And then we denote the operator algebra in this quantum field theory in the curved space-time, say in the right region, say outside the horizon to be m tilde r, and the one for the left region to be m tilde l. So the standard story for the duality outside the horizon then could be formulated in the following language. Is that we essentially, so we identify this GNS Hilbert space around the thermal field double state, and then the Fock space around the black hole. Okay, around Fock space around black hole. And then you identify this, say this GNS vacuum which is essentially the representation of the Sommerfeld double state in the GNS space and the Harder-Hawking vacuum state. And then you identify the operator algebra, say single trace operator algebra in the boundary theory with the single trace operator algebra. With the algebra generated by the Bach field, say the outside horizon, and similarly for the left theory. Okay. So diagrammatically, it's like this. Say we understand reasonably well using the standard CFT, ADS-CFT, the story outside the horizon, and then we can establish this correspondence between the operator algebras in the boundary theory and in the Bach. Okay, but this identification itself does not directly tells you that the reason I put the question mark here does not directly tell you whether there's a future and the past region and how this right and L region are connected in what way. Okay. So, but if you believe the standard, say duality with the internal black hole, and then this M tilde MR, M tilde R, and M tilde L, they just operate the algebra for quantum field theory in the curved space-time in the sub-region of that space-time. Okay. So from the standard story, we believe that algebra is actually type 3-1 of von Neumann algebras. So, and if we want this duality to hold, and then this MR and ML, they had better to be, say, type 3-1 von Neumann algebras. Okay. So here I want to emphasize a very important point, a simple but a very important point regarding the single trace, this operator algebra generated by single trace operator in the infinite end limit. So let's consider a causal diamond, say in the space-time. So if you consider consider the operator algebra associated two Cauchy slices, say for this diamond, okay, so A1, A2. So if you are in the standard quantum field theory, and then A1 are just equivalent to A2 because they can relate it by Heisenberg evolution. So any operator on A2, we can express it in terms of equation motion in terms of those on A1 and vice versa. But for algebra of single trace operators, this is not the case. So A1 is not equal to A2. So the reason is the following. So if you try to use the Heisenberg, if you take the single trace operators, say on A2, and involve back using the Heisenberg equation, you will get some very complicated operator on this A1 slice. And that's not outside the standard single trace operator algebra. Okay. So a single trace operator algebras A1 actually are not equivalent to A2. So this will play a very important role in my discussion below. And so also for this reason, this MR and ML, which are defined as single trace operator algebra for the boundary theory in the infinite end limit, they should be understood as defined on the full boundary space-time. Okay. So this identification algebra then leads to a rather curious structure. So let's just use this to denote, let's just view, for simplicity, let's consider the boundary just two dimension, say 1 + 1 dimension, say the horizontal vertical axis is time, the horizontal axis is a spatial direction, so we can consider to be a circle, and then this will be identified. And so we have the right algebra and the left algebra, single trace operator algebra, they're defined for the full boundary space-time. But in the Bach, we actually have an ordinary quantum field theory in the curved space-time. Okay, so this operator algebra, in particular, this operator algebra M tilde R and M tilde L can be defined on a single Cauchy slice. Okay, so that means that this algebra defined for the full space-time MR actually is mapped on the single Cauchy slice, okay, and to the Bach, okay, to the Bach. And so in particular, this MR already include time, okay, already include time. So that means actually when we think about this relation, we actually need to rethink what we, sorry, there's misprint here, what we mean by boundary time, okay. in particular, how this boundary time are related to the Bach time, because in this correspondence, this MR already including the full time. Okay. And so if we think about, so now let's think about some kind of evolution, say like Kruskal kind of evolution, just say suppose start with t equal to 0 time slice. You want to smoothly evolve into some other time slice, say which cross the horizon, okay? And then from the standard story, this evolution will be essentially isomorphism of algebras, which maps to the algebra on this slice to the algebra on that slice. Okay, this is just as the standard in quantum field theory. So the algebra on these two slices are equivalent, and then they should be isomorphic to each other. So then this means, okay, the Bach time evolutions should correspond to the bound, but in the boundary theory, as emphasized, MR and ML already involve the full space time. Okay, they're already defined on the full space time. So this Bach time evolution actually should be then understood as some kind of boundary automorphisms, say of this the union of these two algebras. Okay, and it's no longer obvious that how the boundary time is related to some kind of Bach time. Okay, so now you have to think about what kind of automorphism you should allow in the boundary theory, etc. And then the question is, what kind of automorphism, say in the boundary theory, actually corresponding to the Bach time evolution? So I will try to answer this question. So do you have any questions so far? Yes.
Go ahead.
All right, I had a question when you said something earlier a few slides ago was very important. Okay. That the two algebras, A1 and A2, were different.
Yeah, that's right. Yeah.
What invariant of the algebra can you compute that shows that they're not isomorphic? You meant by not equal, I assume you mean that they're not isomorphic as von Neumann algebras. So what invariant can you compute that distinguishes them?
Yeah, I cannot really answer that question. The only thing I could say is just say I no longer have the standard story.
Oh, I see. You're just saying that the argument in QFT doesn't apply anymore.
That's right.
So you don't know that they're equivalent.
Yeah,
it's
right.
It's not that you know that they're not equivalent.
No, I cannot. I'm just saying the standard argument saying they are equivalent no longer apply, and I strongly suspect they are not equivalent. But I don't have. I don't have. At least for myself, I don't have such a proof. As you mentioned, some kind of precise mathematical way to show they're not isomorphic to each other.
If I could say a word, isomorphic is the wrong question. They are isomorphic because they both are type III1 algebras. But that's a useless statement. What you want to ask is whether there's a natural isomorphism between them. And there's none. The natural one would have been time evolution. And as Hong says, that's not available here.
Okay, good. Thanks. Thanks, Edward. Yeah. Mm-hmm. Good. Okay.
Hong, I'm sorry. I have a question too. I'm getting a little confused by your identification of the boundary algebras with the bulk algebras. So if I look at this Cauchy slice, the algebra in ordinary quantum field theory, without even worrying about gauge invariance, the algebra of operators on that Cauchy slice is not a tensor factor of ML twiddle and MR twiddle. But on the boundary, ML and MR, that's definitely a tensor product algebra. So where
good. Tom, that's a very, very good point, which I should have emphasized. Indeed, this is the key in the Bach. You cannot tensor factorize M tilde L and M tilde R. And indeed, because of this type III1 structure, because MR and ML act on this GNS Hilbert space around the Sommerfeld double states, and because of the type III1 structure of them, they also don't have a factorized structure. So you have so even though at the finite n, the operator algebra are obviously factorizable, but in the infinite n limit, MR, ML can no longer be factorized.
I see. Okay, thank you.
Yeah.
I hate to interject with another comment, but what doesn't factorize is the Hilbert space. The operator algebra is the product, or a completion of the product, as Hong said. When Hong says that the bulk operator algebras are type 3 factors, that's precisely a statement of the non-factorization of the Hilbert space.
Right, yeah. Yeah, they can no longer be associated with, say, individual factorized Hilbert space. Yeah, that's the way to say it. Good. So let me just mention some well-known, some immediate candidates for boundary automorphisms. Say the one, the first one immediately come to mind is the HR minus HL. And so this is actually the modular evolution, say, which say appears at the finite end. So if you in the Sommerfeld double state, and then the modular operator associated with the Sommerfeld double state, say for the right or left algebra, is the HR minus HL. What's interesting is that this HR minus HL also have an infinite n limit, so well-defined infinite n limit. So that will also persist to be a modular operator, say on the the modular operator in the infinite n limit on this GNS Hilbert space. And so of course this leads to the well-known flow of the Schwarzschild time in the bulk. Okay. And so this is automorphism, say in the boundary theory. And another maybe candidate which people may think about is HR plus HL. But HR plus HL actually does not have a well-defined limit, an infinite n limit to act on this GNS Hilbert space. Okay. In fact, the only combination of HR and HL which have a well-defined infinite n limit is HR minus HL. Okay, and so there's various arguments for this, both from the boundary or from the bulk point of view, etc. So we're not going to that. It's just one thing you can see from the, for example, in the bulk point of view, that if you naively act on this on the operator, on the Cauchy slice, and then you actually generate a kink, okay, at the horizon. So any combination of HR plus HL, other than this modular evolution, actually now is no longer a candidate for the bulk time. Okay, at least in the infinite limit. So now the latter question is that now if you want to ask this kind of smooth time evolution from this t equal to 0 slice to some other slice.
Sorry, I have a question about this. So I think I'm not sure I agree with this. So
okay.
So if you have this h left plus h right, these are the Hamiltonians in the full boundary theory?
Yeah.
Yeah. So, I mean, I think that when you act with this operator, you're just translating the whole diagram up and down. So you made a statement. Well, the statement I don't agree is that it creates a kink. That's what you said. So I think you're just, you have the same diagram you had before, but time now is, the zero equal time equal to the whole diagram is displaced up and down. It's just there's maybe I should say this.
Moving the Cauchy slice up and down.
Yeah, but the question is what happens?
The Cauchy slice is irrelevant because we should be talking about the state, right? So the state is changed, and in the state is just the same state that you would have when you move the times forwards on the boundary, right? So it's some other state.
Yeah.
The state is not invariant. It's just the original state is transformed into some new state. And in this diagram, what happens is that the state that results from acting with h left plus h right is it's just the same diagram, but where the boundary times are identified to the coordinates in this diagram in a different way.
Right, right. Yeah, there are several levels you can talk about the action of this HR plus HL. So, so certainly, say if you have a finite but large n, this action is well defined as what you are saying. This just translates the boundary time upside down. Oh yeah, up and down. But now I'm asking a more specific question. So I'm asking its action on the GNS Hilbert space, or its action on this Fock space in the block, the Fock space in the block in the say G Newton goes 0 limits. And that one, if you say just act this say on the operator algebra here, and then you will create a kink. And yeah, so this is a more specific statement.
Hong, I feel instead of claiming the kink, what you should say is that.
Sorry?
What I think you should say is the following. The
Okay.
two pictures on the left and the right, the second one where you've moved forward the boundary cut, they in the large n limit, they correspond to different GNS Hilbert spaces.
Yeah, it's true.
I think that's the way you should phrase it.
Yeah, certainly.
For finite n, they'd be different states in the same Hilbert space. In the large n limit, there are different states in different, there are states in different GNS Hilbert spaces.
Right, yeah.
That would be
that
a
agree.
way to say what you're saying.
Right.
I think the thing that's puzzling is that if HR and HL are the ADM Hamiltonians, then all we can really say is they move the endpoints of that surface upside down, up and down. We can't say anything about what's going on in the middle of the slice, because indeed you can just do a gauge transformation to move around the middle of the slice. So I definitely wouldn't say, even in the classical limit, that H right plus H left generates a kink. I think that's incorrect.
Yeah, so to be able to talk about the interior, you have to be more specific, ask a more specific question. I think what Edward pointed out an important point, which I should have said, is that if you act HR evolution of HR HL on the sum of your double states, that will create the states outside your GNS Hilbert space. Yeah.
But aren't we defining this Hilbert space too narrowly, given that the state has a manifestly clear gravity description? The state that results from acting with H left plus H right has a perfectly fine gravitational description in this diagram.
Yeah. I think I don't think what we are saying are contradictory with each other. It's just saying you say you can act this on the sum of a double state, and then you can create a state whose block geometry can be closely related to this one. And here I'm just talking about more specific questions. I want to find operators, find automorphism which can smoothly evolve this block operator algebra. Okay, so I claim that does not do the job. In this GNS Hilbert space based on some of your double state. Good. So that means now this thing somehow has to be emergent somehow. Okay. We don't have our usual candidates at our proposal. And also it's clear that somehow such an operator must involve non-trivial couplings between CFTR and CFTL. So if you want to create a smooth evolution of a Cauchy slice at t equal to 0 to some future slice. Because you have to start with operating in the right region, and then you will take it inside in the future region. And once you are in the future region, and then we'll in causal connect with the CFTL and the CFTR. And you cannot do that just with this kind of factorized Hamiltonian. Okay, there's no way you can do that using the factorized Hamiltonian. So the generator must involve a non-trivial coupling between CFTL and CFTL. So this is both forced on us by the infinite n structure and forced on us by the geometry. Okay, if this geometry have to be the right answer, and then this forced on us. And so we will see that this emergent type 3-1 structure actually will give us an answer to this. So give us to this emergent times, also sharp horizon structure, interiors, and associated causal structure. So yeah, so the tool we're going to use is that for type 3-1 von Neumann algebra structure, there's a very special thing associated with this type 3-1 von Neumann algebra. So this is called half-sided modular translation. So here I have to use a little bit of mathematical language. So let's imagine you have a von Neumann algebra and then some vector omega. So here this von Neumann algebra, say for our case, would be MR would be, say, the von Neumann algebra for the single trace operator algebra on the right. And this operator omega would be, say, sum of your double state. And this omega is cyclic and separating for M. It's just the statement, it's the mathematical statement that the modular evolution exists. Okay, so I will just assume the modular evolution of M exists. Okay, so there's a modular operator associated with the M. So now if N has a von Neumann subalgebra N with the following, now let's suppose there exists a von Neumann subalgebra N of the following property, that this is also cyclic for N. Cyclic means just N, that's when the operators act on these states, the resulting space are dense in your Hilbert space. Okay. And then the second condition is that if you evolve this algebra, this subalgebra N using the modular operator, the modular flow of M, it does not take you outside M for half of the flow, okay, for t smaller than 0. Okay, so this is the modular flow associated with M, and the time is the yeah, for t smaller than 0. So if such condition exists, and then the powerful theorem of Bochers and Wisbrock then show there exists a unitary group US with the following property. And then you can say you can consider a generator. There's a Hermitian generator which can generate this one parameter group. And in particular, the spectrum of this operator is bounded from below. And also this operator will annihilate, say, your sum of your double state. Yeah, say the back, yeah, whatever states. For us, will be the sum of your double state. So this G greater than equal to 0 is very interesting. Because as we know, in quantum mechanics, you can have all kinds of unitary transformations or morphisms. But normally distinguish, say, the time evolution with spatial evolution or some other isometries is that the time, the generator for the time evolution is bounded from below. And so we will view this as indication. We can use this to generate new times. Okay, and indeed we will see this will generate new times for us. Okay, and so let me just give you a simple example to illustrate this more abstract theorem. So let's just consider the 1 + 1 dimensional Minkowski spacetime and consider this right Windler wedge. Okay, so the operator algebra in the right Windler wedge is also a type 3-1 von Neumann algebra, just as in the standard quantum field theory. And then in this case, the omega will be the Minkowski vacuum. So I emphasize to define the Minkowski vacuum, you don't actually have to define the Minkowski space or Minkowski time. We can define Minkowski vacuum just using the operator algebra in the, say, Windler right and the Windler left, and then you just give the map of how this omega acts on the act on those algebras. Anyway, so now let's consider subalgebra. Yeah, and then with this Minkowski vacuum, then the modular operator for the Windler right region is just the boost. Okay, so now if we consider this, the operator algebra in this shifted Windler region N. And then obvious N is a subalgebra of M. But also you can show that N satisfies both properties. Yeah, the N is cyclic, it's because of the Rich-Schneider theorem. And the fact that the n satisfy this half-sided inclusion is because if you do the boost on n for then yeah, half of the boost will take n goes to itself. Okay, the lower boost. Okay. Then from this theorem, then that means there's an emergent G, which is bounded from below. Of course, for this case, we know everything. This quantum field theory in the window space-time is trivially we know. And in this case, this G just generates the translation, say, along the x minus direction. Okay, so this is just a light quantum Hamiltonian, say corresponding to translation along the x minus direction. But the non-trivial thing is the following. So now you can see how this U act on original algebra M, and so the algebra in this right window region. So for S smaller than 0, again, this is the boost. Just take M to itself. Okay, don't take you outside M. And in particular, there's some particular value you can take this M to N. Okay. But for S greater than 0, it's obvious you have a null shift, and then you can take this M into the future region. Okay. And so for S greater than 0, actually now you can use this US to generate the window future and the past region from the algebra of the right and L regions. Okay. And in particular, starting with the window time in right and L regions, we can obtain Minkowski time. Okay. So in a sense, just start with the window right and the window left. If you give me this state with the right property, and then actually I can generate the full Minkowski's time for you. Okay. And yeah. So this will be the pattern we use to generate this full internal black hole geometry from the right and L regions of the black hole. Okay, so this should ring a bell. So yeah, so this is a picture. So from the identification of the algebras outside the horizon, we already have this picture. So outside the horizon can be mapped to CFT. The region for CFT for the right region of black hole can be mapped to CFTR, and for the left region can map to CFTL. And now with this US, we should be able to generate the full internal black hole spacetime. Just like that can be used to generate the full Minkowski spacetime using the Rindler. Okay. And so this US, this to new emergent time. And in fact, we will show actually the infinite number of choices of such times. And the choice is far from unique. And such kind of time, by definition, is diffeomorphism invariant. Okay, because it's a intrinsic boundary construction. Okay, so let me just make some general remarks here. So where the theorems of these half-sided modular translations ensure existence of US, but finding it explicitly in general is very difficult. For example, writing down this G explicitly is very hard. Okay. But here we have a simplifying structure. So here in the Lagrangian limit, so the algebra of single trace operators in GNS Hilbert space actually can be described by that of a generalized free theory, generalized free field theory. So in this case, finding this G is actually still non-trivial. Okay, still not easy. But actually there's a shortcut. In this case, even though we cannot find the G explicitly, we can find the action of US explicitly through various constraints. Okay, below on US. So in this case,
I've missed something basic.
Okay.
Here. Why isn't G just the log of delta?
The G is the log difference between the delta of M and the delta of N. So, but the delta of N is in general not easy to, just for the black hole, the delta M is easy to find, but in general, delta N is not that easy to find. Yeah, so you need to find that modular operator. But here you can sidestep that. So you can actually—
So let's see, when you say there are many times, that's because there are many N's?
Yeah, that's right. There are many different kinds because there are many different N's you can choose. Yeah, I will mention some of ends later. Yeah. Good. So in this case, in the when you act on the generalized free field theory, then you can actually constrain the expression of this US to a universal form up to a phase factor. And this phase factor will depend on specific operators. Say this UX act on, say if you act on scalar operator, will depend on the dimension of the operator. Say if you act on, say, vectors or tensors, it will depend on those things. Sorry, my statement is actually on the scale of operator. We haven't done it for the vector or tensor operator, but we suspect that can also be significantly constrained if you act on the tensor or vectors. And for the scalar operators, you can determine up to a phase factor. And this phase factor depends on specific operators and also depend, of course, on the algebra, a specific algebra. Okay, so now let me tell you an example. So remember this ML. So again, imagine this is the boundary for space-time. So the horizontal direction is the time, and the vertical direction is spatial direction, which we can take to be a circle. So these two sides are identified. So the MR, so this M will be the single trace operator algebra defined on the full boundary space-time. And here, as I mentioned, in the thermal field double state, the action of the modular Hamiltonian is just the standard time translation. So now if you consider the operator algebra, say below some time slice, say t equal to 0, okay, let's call this algebra n. So as single trace operator algebras, they are not equivalent. Okay, of course, if you consider the full theory, this M and N are trivially equivalent. They're all equivalent to the operator algebra on the single Cauchy slice. As operator algebra for the single trace operator, they are inequivalent. And N is a sub-algebra of M, and also satisfy this half-sided modular, because here the modular flow is just translation, and just translate this N upside down. So now we can use this to find what's the corresponding US. But finding that phase factor is still not easy, because this is actually a strongly coupled problem. Even though here we are deal with the generalized free field theory, but this generalized free field theory actually comes from an Nigerian limit of a strongly coupled theory. So here we have to use another trick. Okay. So we propose that the operator algebra of N is actually equivalent to the operator algebra of n tilde in this region of the bulk of the black hole space-time. So essentially just draw the causal wedge of this n region in the black hole space-time. And then let's call this region n tilde. Okay, so we propose that the operator algebra in N is actually equivalent to the bulk field algebra in n tilde. So we have some support, various supports, say, of this proposal, which I will not have time to discuss them. Yeah, it's discussed in the paper. And so one thing I want to emphasize, this is more like a generalization of the entanglement wedge. Okay, so the proposal is that for this operator, yeah, essentially once now you start thinking about operators are defined on the full space-time, and the different space-time regions, they have different operator algebras. And that means the way we think about entanglement and wedge have to be significantly rethought. Okay, so here is the proposal for the entanglement wedge for the algebra corresponding to this N. And say, so this does not correspond to some kind of RT surfaces, actually.
Wouldn't you call this more like a causal wedge? Or?
Yeah, I would call it entanglement wedge. It just say it can be drawn simply using these causal diagrams. Yeah.
Well, the thing is that since the argument involves using something like HKLL, so HKLL can only access the causal wedge. So I think. Yeah,
I think you can actually use it more than HKLL. So you can, in the end, you can use modular flows. So I believe in the end, this would be, say for more complicated regions, it would be more like entanglement wedge rather than causal wedge. So here it coincides.
Okay.
Good. Okay, so now based on this equivalence, now you can actually turn, yeah, because now the story becomes simpler because this is until there is really a genuine free field theory in the Bach. And now we can actually use that.
Maybe I'll press on that a little more. So because I'm not satisfied.
Okay.
So in a situation where you have an island, for example,
yeah,
I think that the fact that the Hilbert space has finite 10 is important to say that the entanglement wedge contains the island. And here the construction involves taking first the large n limit and then doing this construction. So I'm skeptical that there could be a statement like that when there are islands.
Yeah, I think it's a very interesting question. I think there's no contradiction with what you say here. When you have islands, so island is still in the leading order in the large N expansion. It's just there you have a different leading order large N expansion. Just when you go past the page time, you have to redo your large N expansion.
Well, I think if you're going to define the operators in the boundary through the bulk, right? And you're going to say that the algebra of operators is the same as the algebra of operators in the bulk in the entanglement wedge, then I agree. But there is no equality in that case. It's just a statement about the bulk operators.
Yeah, but
the hypothesis that they're given by the boundary operators.
Right. Yeah, but I think that we can promote that into a stronger statement, saying that actually the operator algebra they're equivalent. Of course, this is a proposal. Yeah, I don't know how that works.
I think to have an equivalence, you need two different ways of defining the algebra. And so here you're given two different ways. So one way is to talk about the operators in the bulk, right?
Yeah.
And then the other is to simple operators in the boundary that are time evolved. And then you say, well, maybe they are the same. And HKLL gives us a map in this particular case. So I think in this case, it is some definition where you have two sides which are equivalent. Yeah. In the case with islands, I don't see what you have in mind. Maybe you have something in mind that
in islands certainly is a very interesting case, which we don't know how things work out in detail. But I won't say, at the moment I won't say, but I can imagine something can work in the island case, but I don't know how that works in detail yet. So here, I emphasize you don't have to do HKLL. The only thing you need is this extrapolation dictionary. And because you can just do the whatever mode expansion in the Bach, and when you extrapolate, then you can express the Bach operator, say, in A and A dagger. And when you extrapolate that dictionary into the boundary, that A dagger just becomes the boundary operator. And that boundary operator.
That's essentially what HKLL did, right?
Yeah. I'm just saying, just say that's a mapping of the Hilbert space. In the sense you map the JS Hilbert space to the Bach Hilbert space. When you have island, such kind of mapping certainly will become tricky. I don't know how that works in detail yet, but I think it may be possible. Yeah.
No, I agree. It should be possible given the structure of the bulk theory. But...
And part of the complication here is that, the blue thing you drew here isn't really a causal wedge, because the causal wedge would be the whole right exterior in the usual sense of causal wedge. And that in this example, that coincides with the entanglement wedge. So it's hard to have the discussion here.
Yeah, this is like causal wedge for this N region. So it's a little bit,
It's like a restricted causal wedge where you
the restricted,
you're not allowed to use all the single trace operators. You're only allowed to use them below some time. So this is some generalization. I would say this is some generalization of the causal wedge.
Yeah, so that's why I want to say this. Once you start thinking about that this operator algebra in the boundary series defined for the full space-time, that requires us rethink how we really map the boundary under the Bach. And because now the time in the boundaries involved. Yeah. Anyway, you can now do this calculation. Now you can do this calculation. You can calculate what this phase factor is with the help of this n tilde. It turns out that the phase factor just given by the standard phase shift at the horizon. So if you consider the standard story of a scalar field, say a wave equation outside the horizon, say the near the horizon, the past horizon is a it's a plane wave out coming out of the past horizon and the plane wave going inside the horizon. And if you impose normalizable boundary condition at infinity, and then this is like a scattering problem, and then there's a phase shift between the incoming wave and the outgoing wave. And then that phase shift turns out to be given by the phase shift for this US. And and then you can just plug into your universal formula. And then now you have your US. And now we can work this out explicitly for this example for BTZ. Okay, you can just work it out. And then now we can work on see how this act on the Bach algebra. Okay, so now let's take an operator in the right region. Okay, so by definition, this operator is an operator in the CFTR. And so this just follow from the standard dictionary. So any operator in the right region can be can be rewritten as operator in the right CFT, and any operator in the left region can be identified with operator in the left CFT. And now we can just act this US on this operator, see what we get. And then turns out something like this happens. So S equal to 0 is identity map. Then let's take S0 to be. Turns out there exists some sharp value S0 greater than 0. The following thing happen. So for S smaller than S0, this phi xs is still in the CFTR. So the original of this phi x is in the CFTR. Okay, and then you find for some finite range of S is still in CFTR. But then there's this sharp value S0. Suddenly, CFTL operator emerges. Okay, in the evolution. So S0 is like a transition. Okay. And so this is what you expect geometrically when you take an operator to cross the horizon. So suppose you start with the operator here and evolve a little bit, okay? And then of course, if you are still in the right region, then you are still in the CFTR. And then eventually, when you cross the horizon, you of course connect with left CFTL, and then you will then have a CFTL component.
Did you assume?
But I want to emphasize this feature is highly unusual from the field theory point of view. So from field theory point of view, you can have the following two possibilities. You either never generate CFTL, or you generate the CFTL immediately. Okay, so imagine a situation like US is generated by something like HR plus HL. Say something like just direct sum of some linear sum of HR plus HL. And then this will never generate any CFTL because it's commute with phi x. And also, if you take US to be generated by some operators, some arbitrary, some operator which contain generic couplings between L and R, CFTR and CFTL. And whenever, say if you contain such couplings, then whenever you start evolving, then CFTL will immediately be generated. Okay, so here the highly non-trivial thing is that there's a finite interval S0, which this remains in CFTR, and only after S0 CFTL is generated. Okay, and so this is the signature of sharp horizon. And you can show I will not go into there. And this is only possible if you have type III1 von Neumann algebra. And for example, you can show you cannot do this in type 1. Yeah, whether you can do it type 2, I'm not sure. I suspect you cannot. And but in type III1 you cannot. I think in type 2 you can also not. Yeah. Anyway, let me not go into that. So actually here the statement is general. You can actually define it for any two quantum systems. say each choose say some systems which don't even have say holographic descriptions, you can formulate this kind of criteria. So we can say if such kind of US and S0 exist, we can say something unusual happened between these two quantum systems. And we say they're causally connectable in the sense that you can actually jump something analogous to what happens in the internal black hole appears in such kind of systems. Means that you can actually jump into the black hole and they're intact. Okay, and so they're causally connected. Yeah, yeah. Question.
What if you keep evolving?
Sorry.
If you keep evolving.
Oh yeah. If you keep evolving, eventually we'll hit the singularity. Yeah.
And there's an obvious signature of that?
Yeah, that's a good question. We have tried, I believe there should be, but we have tried, but with some technical difficulties, we have not identified a sharp signature yet, but I suspect there should be. Yeah.
Okay, thanks.
Okay, so now let me say a little bit words about this S0 for this particular example I mentioned earlier, this this n given by the half space time. So it turns out in that example, this S0 is given by the following. So now let me just draw the Kruskal diagram, and this U and V are the Kruskal coordinates. And this initial point is U0, V0 with some initial Kruskal coordinate, and the horizon is the U and the V axis. And turns out for that example, this S0 is precisely minus U0. It's the Kruskal-like coordinate distance from this point to the horizon, okay, to the future horizon. But in general, the evolution is actually non-local. But somehow this Kruskal coordinate actually emerges in this calculation. So when we construct this US, we didn't use anything Kruskal at all, okay. And we didn't use Kruskal, it can be viewed as intrinsic boundary theory construction. And now you see that actually this Kruskal coordinate emerges. But this evolution is in generally non-local, means it's not a point-wise transformation. But if you are near the horizon, say if X is close to the past horizon, and then turned out to be a point-wise transformation. So that transformation just gives you the Kruskal U law translation, okay, shift by S. And yeah, but in general, it's non-local. Okay, but even though it's non-local, but exhibit the sharp structure associated with the horizon. Okay, you have this sharp S0, which tells you cross the horizon. And you can probe this question a little bit further. Say, let's look at this commutator. Take a point, say x1 in the right region, and take another point x2 in the left region, and then evolve this operator, and then cross the and then look at the commutator. Okay, so this commutator is non-vanishing if this evolution will enter the horizon, enter the light cone of this x2. Okay, and then you find again this thing is identically 0 for s smaller than u1 absolute value plus u2. This s u1 absolute value is just the normal distance again along the u-axis from this x1 across the light cone of x2. Again, this just come really it just from the boundary emerges, and then this becomes non-zero when s greater than u1 plus u2. Yeah. So that's this shows that actually even though evolution is non-local, but actually preserves sharp causal structure. But there's another surprise.
Excuse me, Hung. In these formulas, when you say that S has to be bigger than U1 plus U2, have you assumed that the field you're considering is rotationally invariant?
For this one, we don't have to. For this one, we don't have to. Yeah, this can be general.
Okay, thank you.
Yeah, the next statement requires. Yeah. So now you can look. So in general, this transformation is rather complicated. Even for BTZ, involves some heterogeometric function, etc. But of course, the action, as I mentioned, will depend on the operator itself, depend on its operator dimension, etc. It turns out when you take the operator dimension to be very large, and turns out that the action actually simplifies. So it turns out when you take the operator large always means the parametrically large of order 1. Okay. So when you take it to be large, it turns out the evolution become a pointwise transformation. So this is some complicated expression, but you can rewrite it as the expression of phi evaluated at some Bach point, say in gravity side. Okay. And for this to be true, we actually have to average over the boundary spatial direction. And so this expression is very complicated. So to be able to write it as a pointwise transformation is a highly non-trivial statement. So we could only do it when we average over the boundary spatial direction. I don't know whether this still happens when we don't average, or this just fails when you have spatial dependence along the boundary directions. Anyway, so if you average over the boundary spatial dimension directions and take the large mass limit, you will see this. And then this xs turns out again to be expressed in a simple way in terms of Kruskal coordinates. So this so xs, the Kruskal coordinate, is related to the original one by the u coordinate by shift by s, and the v coordinate by this transformation. So this transformation have the following feature for v. Near the horizon, say v0 equal to 0, this does not transform. So this then just reduced to a pure u translation. And also vs is such that this takes a boundary point still at the boundary. Okay, so the boundary point still remains on the boundary. So so this v have the following feature. Anyway, so we can draw the flow pattern now. Just take a point in the block, and you can see how this flows. Okay, and if you look at this formula, it will say it hits singularity at some finite value of s. Okay. Anyway, so this is also constant s slice. Oh yeah, I didn't realize I'm way past time now. Okay, sorry. Yeah. So if you act on the constant time slice, and then will be like this. And then the flow, then it take you from this coherent surface to that coherent surface, etc. And you can also look at other possibilities. Say if you take n to be, say, the sub-algebra above some time, and then we argue it can be dual to some wedge like this, and then again you can construct flow will be like this. Will be, say, near the horizon will flow along the v axis. Okay, so we call this v type of flows, Kruskal v type flows, and then the Cauchy slice will change like this. And we can also consider compositions of such Kruskal u and v type flows. So in principle, the infinite number, there's an infinite type of this kind of infinite type of flows. Okay, you can also construct time space-like flows. Yeah, because if you anyway, so you can also do non-homogeneous in the spatial direction, etc. Say below some time, above some time. You can also change your states a little bit. So there are many possibilities. So let me just finally quickly mention this type III1 von Neumann algebra actually are not restricted to Sommerfeld double state. It's actually generically present in the gravity on the boundary theory in the infinite n limits. So let's just consider the case which is the boundary CFT in the vacuum state and considering some region R. Okay, so this is some spatial region R in the boundary. Okay, and say let's consider in the vacuum state. Now there's only single copy. So the full operator algebra in R is the type III1. Okay, so this is the standard story. You can consider the causal completion of R, and then the operator algebra associated with that causal completion should be a type III1 von Neumann algebra. But now we consider infinite n limits, and consider the single trace. Again, consider single trace operator. And then the completion of single trace operator algebra in the causal completion of R. So by completion, we mean the say take the double commutants for the R restricted to the causal complete. For the algebra restricted to the causal completion of R. then you can argue it's actually an emergent type III1 algebra in the large element. So there's a simple manifestation of this type III1 algebra on the gravity side. Yeah, so now we have actually two type III1 algebras. So there's a simple manifestation of these two. So for the first one, it just relates, yeah, because for the first one means that your entanglement entropy is not quite well defined. You have to introduce a short distance cutoff in the boundary theory in order to describe the entanglement entropy. So that's reflected in the standard divergence in the RT surface when you approach the boundary. Say if you look at the RT surface associated with some boundary region R. And this second type III1 von Neumann algebra then is reflected when you calculate the entanglement entropy in the region, in the entanglement wedge, okay, in the bulk. And then there's then there UV divergences associated with the RT surface. So this divergence reflect this type III1, this new type III1 von Neumann algebra. Okay, yeah. So this type III1, so this emergent type III1 von Neumann algebra also have many implications. Okay, so let me just quickly mention some further directions which we are considering. So, for example, you can try to use to probe the singularity. So a black hole singularity, the slogan is that somehow the black hole singularity signal that you cannot extend this emergent type III1, say arbitrarily to large parameters. Okay, so this is a gravity way to tell you somehow this type III1 algebra is emergent. And so also this spark UV divergences, yeah, so this type III1 algebra also will give us new insight, yeah, can in principle give us new insight into the nature of the bulk UV divergences and emerging the black hole area term, and also more general notions of this entanglement wedge construction I mentioned earlier and associated entropies, say whether there are new entropies associated with this more general type of entanglement wedge. Also the signatures of horizon for, say, simulating quantum gravity in the lab, and also may provide hints for emergence of time in cosmological space-time like de Sitter. And also actually you can use this, you can show actually we are finishing a paper right now. You can show actually this can be used to understand where does this quantum arrow correcting properties on the gravity side emerges from the boundary theory. Yeah, since I'm out of time, let me just stop here. If people want, I can say a little bit more regarding the last topic anyway, but yeah, but let me just stop here. Yeah, thank you.
All right, let's thank Kong again. We asked a lot of questions during the actual talk, but are there any questions now? And I remind the locals that we'll get back together in around 15 minutes or so to keep chatting.
I have a question. This is Steve Schenker.
Okay, hi, Steve.
Could you imagine computing some of these things directly in the boundary theory at very small Latouth coupling using some perturbative calculation?
Yeah, in principle we can. Yeah, in principle should be possible, but that requires calculating this kind of modular operator for this sub-algebra associated with half space-time.
Yes. I
don't know how complicated that is. I suspect it would be non-trivial, but I have not thought carefully about it. Yeah, maybe for SYK could be maybe the simplest place to start, I would say. That might be possible. Yeah, maybe even maybe one can. Yeah, my suspicion maybe one can already reinterpret some of the current SYK calculations. People have done lots of SYK calculations, and in this language. Say maybe that kind of a modular operator for that half space can be calculated using some replica trick. We can get some insight on that. Yeah.
Okay, thank you.
I have a comment on something that came up at the beginning of
Okay.
it. You talked about the Hilbert space for a time slice of the boundary. And then you talked about the Hilbert space for a later time slice. And the assertion was that the two GNS Hilbert spaces are different. They both have natural gravity constructions. What it means to say that they're different is that you can't take an inner product of a vector in one space and a vector in the other space. For finite n, you can, but at n equals infinity, those inner products are 0.
Right. Right. Yeah. Yeah, that's right. Yeah.
Any other questions? All right, if not, let's thank Han again. And again, the locals are interested. We'll meet up in around 15 minutes. Okay, thanks a lot, Han.
Okay. Okay. Thanks. Sorry, Lima. We meet at what time exactly?
Around let's say 4.
4. Okay. Yeah. So so I have to
you-
leave around 4:20. Yeah.
Yeah. We'll just chat for 15, 20 minutes, and we'll let you go. I promise.
Okay.
You have the link, right?
Yeah, I have the link. Yeah.
Okay, terrific. All right, so see you soon. Thanks
Okay.
again.
Yeah. See you soon.
Bye.
Yeah, bye.
Bye.